So in this clip, we're going to be looking at ways to simplify or find a simple version of the matrix of a transform. So the idea is that given an operator, we want to know that we can find a basis for which the matrix of T is simple and easy to work with. And so one extreme example of this is that if V has a basis of eigenvectors, eigenvectors of T, then you can find, then with respect to that basis, the matrix of T is going to be a diagonal matrix. Because a diagonal matrix just implements a scaling, right? So when you multiply by some matrix that looks like this, and you multiply, so if you multiply any vector that looks like, say, you've got a 1 in some coordinate, then whatever coordinate that 1 is in, it's going to be scaled by lambda of that coordinate, right? So that's about as simple as you can get. That's more simple than you can expect part of the time, but we can still hope for something nice, which is that for an operator on a finite dimensional and complex vector space, V has a basis for which the matrix of T is upper triangular. So that means that the matrix for T looks like something where we've got entries up here and then 0 below the diagonal. Or we'll see this written sometimes. We'll write the diagonal entries as lambda 1, lambda 2, etc. And then we'll put a 0 here for all the zeros below the diagonal, and then a star here for all the stuff that's whatever the heck it wants to be above the diagonal. And so the technical definition that we're using for what it means to be upper triangular is that if J is strictly larger than K, then the jkth entry of A has to be equal to 0. And we're also looking at a matrix which is definitely square, since we're looking at an operator on V. So it has the same dimension as the range the domain and the codomain have the same dimension because they're the same space. So we have a square matrix for this guy. Okay, and so the next result is not in the textbook, but I think it sort of helps to illustrate the ideas that come in the following proofs. So the idea is that the upper triangular matrices form an algebra. And so actually we can simplify the proof by noticing that this is they form a subalgebra of FNN. Okay, and so let's see. If we have two matrices A and C, and they are upper triangular, then it's more or less clear that A plus C and lambda A are also upper triangular. So what do you have to do? You just have to check the elements below the diagonal are 0. So what's something below the diagonal in A plus C? Well, it looks like a below diagonal entry of A plus a below diagonal entry of C, so that's going to be 0 plus 0. And then similarly, or even more simply for scalar multiplication. So in order to get that this is a subalgebra, all we need to show is that also A times C is upper triangular. So let's see, so what do? So we look below the diagonal. So this is where J is greater than K because we've gone further down than we have across. So that puts us below the diagonal. And then we check the jkth entry of the product, which we have the handy summation formula for. So as L goes from 1 to N, this is AJLCLK. And then to see what happens in this expression, we really need to look inside the matrix a little bit. So I'm going to do a little doodle of what AC looks like. So here is our upper triangular matrix A, and then here is our upper triangular matrix C. So we've got something where there's non-zero entries here and non-zero entries here. Okay, and so now let's see, we're going to look at say the jth row times the kth column here. And so notice that I've picked them deliberately here where J is further down than K is across, because we're looking for an entry that's below the diagonal. So this would so this would correspond to whatever's going on in the product down like here somewhere ish. So there's J, K. Okay, so now if I write out that right, so that entry is going to be given by the dot product of those two, that row vector with that column vector, yeah? So if we look at that row vector, so this is J comma dot, then what does this look like? Well, it's going to be 0, 0, 0, 0, all the way down until at some point we hit the diagonal. So that'll be right here. And so that's going to be A, J, J is the first time we get something that's potentially non-zero. And then so we have A, J, J plus 1, A, J, J plus 2, etc. up to A, J, N. And if we look at that column vector from C, I'll write it here as a transpose. So we've got C dot comma K transpose would be written as, and so then we start off at the very beginning with C1K, and this goes until we hit the diagonal here, and that's going to be at CKK. So we have CKK, and then we're out of the zone where C has entries, so it's going to be 0 all the rest of the way. So now when we do, so there's the key point to notice here is that here's the K where the kth entry where the C's end, and here's the jth entry where the A's begin, and we've got that J is bigger than K by assumption. So there's a strictly positive gap between these entries here. And that means that when we compute this sum, we're going to have a bunch of things that have 0. And then it might be the next one where we find the a's, or there might be somewhere we've got 0 times 0, depending. So these ones may or may not appear. But then we would have the A, JJ, and the C's are definitely still 0 out here. And so since every term in that sum has at least one factor of a 0, the whole thing adds up to 0. And so the entries below the diagonal are all 0. And so there we go. Now, the main reason I had for wanting to show you this proof is exactly this idea that you see right here, kind of, where when you've got an upper triangular matrix, the way things line up, something can get killed off entirely.